Hi, so before we can prove the formula and the theorem on the option pricing hedging strategy, I'm going to prove you a simple lemma. I'm going to write up and prove a simple lemma. This lemma will show that the probability space is so simple that essentially every martingale can be written in terms of some prototype martingale. Okay, so first I'm going to make a definition. Zn is going to be defined as the sum of omega k minus 2p plus 1 from 1 through n. And this is still living on this simple probability space we have. So remember that we have IID omega i's, which are plus minus 1s, plus 1 probability p minus 1 probability 1 minus p. So the expectation of the omega I, the mean of omega I, is p minus 1 minus p, so it's 2p minus 1. I'm exactly subtracting that mean, so these omega k minus 2p plus 1s, these are still IID of course, and they are mean 0. This minus 2p plus 1 exactly makes them mean 0. If I add up IID mean 0 random variables, that's always a martingale. And the lemma I'm going to show you now, and which we'll need in the proof of the pricing formula, is that any martingale, let Mn be any martingale in that probability space of omega f. I'm going to put here the filtration which we had before, and p. So this is just the filtration which we had in the probability space, so that's just the filtration generated by these plus minus 1 omegas. Any martingale in here is going to be a martingale transform of that z. Okay, so for any martingale we have, then there is a unique predictable process which I'm going to call age, such that M is just the martingale transform, well there might be an M0, and the martingale transform of Z, of this Z here. Okay? Let's write this out so that we have the formula in front of us. It's the sum of k, age k, times the increment of z. So zk minus zk minus 1. Okay, that's, oops, this is m naught plus. That's what the martingale transform means. Okay? And in order to prove this, we're just going to do brute force. So the proof is going to be brute force. This sample space is so simple that everything is just calculable explicitly. So the proof by brute force is the following. Okay, so let me start off with writing up mn minus mn minus 1. So I'm looking for age. I'm looking for age which does the following. If I look at the difference of the above for n and n minus 1, then I can just write, so m naught cancels, and I can just write the sum from 1 to n and the sum from 1 to n minus 1. Okay. And clearly everything cancels except the last term, so I have the last term of this sum which survives hn, zn minus zn minus 1. This is what I want. I really want this, right? Because I want to find h which satisfies this. Okay, and I want to write this out a little bit more. So what is zn minus zn minus 1? Well, z itself was a sum. So if I look at the sum up to n minus the sum up to n minus 1, then the difference is just the last term. So this is really hn times the last term, omega n minus 2p plus 1. And let me just expand this a little bit more. So let me expand this a little bit more. There are two cases. It could be that omega n is 1, in which case I have 1 minus 2p plus 1, so that's 2 minus 2p. And let me add here the indicator that omega n is 1. Or it could be that omega n is minus 1, in which case I have hn times minus 1 plus 1, they cancel, so I have a minus 2p here. And let me add here the indicator that omega n is minus 1. Clearly these indicators are summing up to 1 because the events are exclusive and they span the whole sample space. So either this happens or that happens, and in this case this factor becomes 2 minus 2p, in that case this factor becomes minus 2p. Okay, now any function, any random variable in a probability space is just a function of the omegas. Remember that random variables are functions on the probability space, on the sample space. So any function is just a function of omegas, and hn is a function of mn minus mn minus 1. So I'm still going to assume what I want. So I want to find h that satisfies this. This whole proof is kind of a reverse engineering process. So if I accept that this should hold, that will tell me what hn actually has to be. So hn, and I'm going to write it out explicitly as a function. At this point, I don't know whether it depends on omega n or it doesn't. This formula just tells me that it's a function of mn and mn minus 1. Mn is adapted, so it can depend on all the omegas up to n. So at this point I need to assume that h depends on omega n as well. We'll comment on this later. But if I assume that it depends on omega n as well, then I'm going to break this equality above into two cases, namely omega n is 1 or omega n is minus 1. So if omega n happens to be 1, so this is really a function of omega 1 through omega n minus 1, and the last variable of this function is plus 1. In that case, I have this indicator and I don't have that indicator. Okay? And in that case, I can just read off what h has to be. It's that difference here over 2 minus 2p. So I'm going to write out that difference, mn. And again, I'm going to explicitly write out that mn is a function of the omegas. So it's going to be a function of omega 1, omega 2, and omega n minus 1, and then omega n, which is assumed to be 1 if omega happens to be 1, omega n happens to be 1, minus mn minus 1, which must be a function of omega 1 through omega n minus 1 only by being adapted, and then I have to divide that by 2 minus 2p. So if this is the case when omega n happens to be 1, okay? So if omega n is 1, then I have this line. If omega n is minus 1, then I am going to write out a similar line for that case. So if omega n is minus 1, and probably it makes sense to use a different color for that. So if omega n is minus 1, then I still have hn of omega 1 through omega n minus 1. This time the last variable is minus 1, and it equals to, so again I'm going to write out omega n as a function of the first n minus 1 guys, and omega n is minus 1, so mn is a function of these, and the last variable must be minus 1. Minus mn minus 1 is just a function of the first n minus 1 variables. Now this time this indicator will be 0 and this indicator will be 1. So I have to divide by a minus 2p this time. Okay, so I have to divide by a minus 2p this time. So that's the other case when omega n is equal to minus 1. Okay, now at this moment, assuming that my Martingale can be written in that Martingale transform form, I did reverse engineer what age n is, but there is a problem. The problem is that I need to have a predictable age n, and this age n seems to depend on omega n. Predictable means it can only depend up to omega n minus 1. It cannot depend on omega n. However, here it seems to be different. These are different formulas for omega n equals 1 and omega n equals to minus 1. So I'm not done yet, because the process I found is not predictable at this moment. I need to actually show that this thing is in fact predictable. And that's what I'm going to do next. Okay, so let's just save these formulas. And next what I'm going to do is show you that actually this age will not depend on omega n. It just looks like it, but really it does not depend on omega n. So what I'm going to do now is, why is this thing predictable? Okay, so I need to show now that age is indeed predictable. In other words, does not depend on omega n, only on omega 1 through n minus 1. Probably I'll use a different color because this one is going. Okay, so one thing I haven't used that yet is that m is a martingale. So far what I did was true for any random variable mn, any process mn. I haven't used that it's a martingale yet. So let's use that it's a martingale. So use that mn is a martingale. So how am I going to use that? Well, what does it mean to have a martingale? So mn minus 1 has to be the expectation of mn given fn minus 1. Okay? Now, what is this conditional expectation? So I'm fixing the sigma algebra fn minus 1, meaning that I fix all the omegas up to n minus 1, and I'm doing an averaging with respect to the last omega, the nth omega. So it's an averaging. This conditional expectation is an averaging with respect to omega n only. Let's write this out explicitly. So it's an averaging with respect to omega n only. Now, what is omega n? So omega n is 1 or minus 1, plus 1 or minus 1 with probability p or 1 minus p. And this conditional expectation is an average with respect to those two values. So let's write that out. With probability p, I have the martingale at omega 1 through omega n minus 1, and with probability p, omega n is 1, so omega n has to be 1 here. And with probability 1 minus p, with probability 1 minus p, the martingale has its variables, except that the last one is minus 1, is fixed at minus 1. So I broke up this conditional expectation. I just wrote out what this conditional expectation is. Okay, so that's my left hand side, that's my right hand side. So I'm going to now rearrange this a little bit. mn minus 1 can also be written as p and 1 minus p times mn minus 1 together. So if I do that, then I'm going to keep the 1 minus p bit on the left hand side, and I'm going to do something else, and then I'm going to take the p mn minus 1 on the right hand side. So far, if I put this back to the other side, then I just get mn minus 1. And the 1 minus p times mn at omega equals to minus 1, I'm going to pull on the other side. So I'm going to have here 1 minus p times with a minus sign, as this goes left, m of n at omega 1 through omega n minus 1 and omega n equals minus 1. Okay, so all I did was I put this on the other side and I kept 1 minus p of the mn minus 1. The remaining p of the mn minus 1 is already there, and I'm going to keep this part here. So I'm going to write p times mn omega 1 through omega n minus 1 and omega n is plus 1. I'm going to actually pull that p out in front and I arrive to here. Okay, and now I can further write this as well, let me write it in the following form. I'm going to divide over by 2p1 minus p. I'm going to divide over by 2p1 minus p. And I'm also going to change the order here. So I'm going to write a minus mn omega 1 through omega n minus 1. Omega n is minus 1 minus mn minus 1. Okay, I just copied this line here, so this part here. So far I divide by 2p1 minus p, both left and right. If I divide by 2p1 minus p, that will give me a 2p down here equals to. I'm going to keep the way I wrote this bit. I'm keeping this part. Divide through by 2p1 minus p, but p is already there, so it's just 2 1 minus p. Okay, and now if I did everything correctly, then hopefully we'll get something nice out of this, because if I look at mn at omega equals 1 minus mn minus 1 over 2 minus 2p, that's exactly this right hand side here. So this thing here is that line, and if I look at minus 2p dividing mn at omega equals minus 1 minus mn minus 1, that's exactly the left hand side. So this bit here is the same as that bit there, and that exactly tells me that Hn at omega n equals to 1 is the same as Hn at omega n equals to minus 1. Okay, so this equality here, the green thing, exactly tells me that these two guys are equal. So I'm going to go back to this sheet now, and I'm going to continue based on my green observation. I'm going to continue with the fact that these two are actually equal, and that's again coming from my calculation in green. So these two are the same. So that means that this is really just a function of omega 1 and omega n minus 1, and it doesn't care about whether omega n is plus or minus 1, because the formula I got is really equal in the two cases. And so this function can be expressed either this way or that way, and it follows directly from what my martingale was. So it's, if you tell me what the martingale is, then this is the predictable process which I should define, which makes this martingale into the martingale transform of z, of this simple z we had up here, of this simple z. This predictable process will transform that z via a martingale transform into your martingale. Okay, so that's the lemma. If you give me a martingale, then here is the predictable process. This one here is the predictable process, which transforms the simple martingale z into that martingale you gave me.